There we go. Thank you, thank you, thank you for letting me know. Whew, okay. Well, the good thing is, because I used, I made, well, the browser saved all the pages anyway, so I didn't have to restart a whole bunch of stuff. Once I get back in, I have, all the tabs in. It's even on the same active tab, so that is nice. And I only got one more thing to do, which is to show the tablet screen because it has a graph that we're going to work on today. And I need to do it one more time because the first time the connection to the VNC server somehow is not persistent. So I'm gonna do it one more time. There we go. All right, so this is a good example of a graph that and the associated H function. So I'm just going to put it into view right here so you can see it. There we go. All right, so we have a graph. This time we only have 5 vertices instead of 6, but it's still good as an example. So the edges has the distances. So the distance from A to C is 5, from C to D is 4, from B to C is 3, and so on. So that part we know already. But what is new is the heuristic function. So in this case, the heuristic function is defined to be from A to E is defined to be 9. Okay, we got some people typing. I'm keeping an eye on that. Oh, you cannot see the stream. Oh, right. Okay, that's why. That is because I did not turn on screen sharing. Operator error. There we go. So let me do it one more time. Let me get out of the screen share again, and oh, I can just change stream quality on the fly. Oh, okay, that's cool. Because I don't want to use the maximum resolution because I may not have the bandwidth to do it. There we go. Okay, thank you. All right, so now that we now that we finally have everything set up, this is the graph that I was just talking about, and it's going to be the example that we'll be using today. We got 5 vertices. We have A to C has a distance of 5, C to D has a distance of 4, A to B has a distance of 1, and so on. So what is new to us are the heuristic function. So technically speaking, you can have a heuristic function, so that it is defined between any 2 vertices. Is the is an underestimate. Okay, it is a okay. I shouldn't say under because under does not include equal. So I have to say it is not an overestimate of the actual length of the shortest path between those 2 vertices. Let me say that one more time. A heuristic function gives you a value. That particular value cannot be an overestimate of the length of the actual shortest path between those 2 vertices. So let's go check out whether these things make sense or not based on that particular criterion. And also cannot go negative. So the smallest value you can use for a heuristic function is 0. It cannot go negative. So let's check out from A to E. So if you look at from A to E, just by looking at the edges, you can see that one side is going to be so the shortest path is actually from A to B, B to C, C to D, D to E. So when you add up all the edges, that would have exactly the same length as 9, which is perfectly okay. Okay, if your heuristic function always has exactly the length of the shortest path between the 2 vertices, then it's the optimal case for finding the shortest path, because you just need to find the dots. You already know the length, so that would be the ideal case, but that's not always the case. So this is the exact opposite. Okay, look at the heuristic value between B and E. So from B to E, which is really just a subpath of what we talked about before, the actual length of the shortest path is 8. But because the heuristic value just cannot be more than the length of the shortest path between B and E, so 0 is actually okay. It is actually perfectly okay as a heuristic value between 2 vertices. Now, does it really help? The answer is no. Okay, it really doesn't help that much, because it's way underestimating. There we go. But we'll see later on that even though the heuristic value seems to be totally useless in this case, it is not wrong. We will still eventually find the shortest path in this case. Between C and E, right here, the length of the shortest path is actually 5, and it is 5 in this case. That's okay, not a problem. And then between D and E, is 1, because E is the destination. So E in this case is our destination vertex. I believe it is being recorded, yes, because I can see on my terminal it's being recorded, and there are a few people on the YouTube side as well. And then the heuristic function from E to E is just 0 because E is right there, at that vertex. So there we go. So now the next question is, how do we make use of the heuristic? Now that part really relies on the algorithm itself. In the earlier part of today's lecture, before my computer, basically stopped working, before it crashed, I sent out 2 links. The first one is a link to the algorithm itself. Okay, it doesn't just bring you to the module, the HTML document. It actually brings you to the A-star algorithm. So hopefully you just click on that one and you will find the algorithm itself. And then the next one is bringing you to the spreadsheet, which is what you're seeing here partially on the screen. So the only thing I'm gonna make, I'll make adjustment for this too, because the only thing that is not gonna show on your screen is the graph itself. So I'm going to take a screenshot of the graph and paste it into the text channel. So you can do whatever you want, with that screenshot. I would just say, open it on the side if you can. Okay, there we go. So now you can open it on your own computer. So this way, when I need to rearrange things on my screen, it's not going to impact, how it's going to look on your screen. So that's kind of the objective of, what I'm trying to do here. All right. So now I can open up the algorithm and put it on the side, and I can refer to the lines of the algorithm, just by counting, from top to bottom, like just the line number, and you can basically match the line, on your side, looking at your own browser. And I will basically try to focus on just the trace, on this side when I'm recording. Alright, so how come BE we didn't use 8? It's because I want to trick the algorithm. That's a very good question. It's a very good question, Anita. The reason why I chose not to use 8 for the heuristic value from B to E is because I intend to trick the algorithm so that it would actually, think there's a better path when there's not. Okay, and I want to show you how the A-star algorithm can figure that out and go like, oh, okay, I thought this was a better path, but turns out it's not the case. So that's why I chose to use a value of 0 instead of 8 in that case. All right. Yep. Okay. All right. So now we're gonna I will start to explain the algorithm. So in Dijkstra's algorithm, we have introduced the L value, which is the length of the shortest path known up to this point. Okay, that's what the L value is, and that's why it gets updated as we run the algorithm. So in this case, we have a heuristic function, which is basically just a very quick function that we can calculate, and it just has to guarantee to be not overestimating. So if you look at the notes, I can just kind of bring that part back in a little bit here. So what the requirement for H is this here. For every V and W in uppercase V, which is the set of all the vertices. In other words, regardless of how I choose 2 vertices V and W, The heuristic function, the heuristic value between v and w, basically it has to be less than or equal to the L value, the actual length of the shortest path between v and w. So that is the restriction of what values we can use for h in this case. So we're going to start with the algorithm. The first part, the first three sentences. Actually, make it the first four sentences. Those are all parameters. Okay, so I'm going to read from the first bullet point. The first bullet point really doesn't need any explanation because at this point we should be used to the notation that G is representing the graph, V is representing the vertices of the graph, and E is representing the set of all the edges of a graph. The second bullet point from the top, we are describing the same thing. D lowercase d is a function. It maps all the edges to non-negative values. So we are trying to figure out, in this case, we're defining what is the distance between two vertices based on the edges. The third bullet point from the beginning, we have one single start vertex in the entire algorithm. So in this case, lowercase s is our start vertex. So A star only works with only one single start vertex. There might be ways to create the illusion that we have multiple start vertices. To be more exact, we can have zero. We can have edges that has a zero distance from one single start vertex to a whole bunch of other vertices. So I have not really looked into whether that will actually simulate the case of having multiple start vertices, but the specification of the A star algorithm is that it only works on from one single vertex to another vertex in the graph. So that will bring us to the fourth bullet point from the top. I use lowercase x as the destination vertex, and there's only one in this case. So unlike my modified Dijkstra's algorithm, which can handle multiple destination vertices, this one can only handle one destination vertices. A destination vertex, not vertices. So those are the four parameters, and we have a fifth parameter in this case. So h as a function is just like d is a function. It is also just a function. In the most general format, it is the domain would be the Cartesian product between v and v itself, because technically speaking, we can compute, or we can try to define the heuristic value between any two vertices. Now, practically speaking, because of the algorithm that we are dealing with, we only need to know the heuristic value from vertices to the destination vertex in our case. So we can basically have a like a simplified version of this h, so that we don't have to worry about every single way to pair up the vertices, and because most of those entries are not going to be useful to us. Alright, so do we have any questions up to this point? I can even, on the tablet, I can show you what I mean by we can have a special case for the heuristic function so that we don't have to deal with that. So if you focus on the tablet right now, I'm just going to write a new description for our h. Oh, okay, wrong tool, because I was using the select tool earlier. Okay, so our h function can start with, it's still a two tuple, but I'm not gonna, the first one is still v itself. It's still uppercase V, which refers to all the vertices in the graph. Now we still have a Cartesian product, and then the trick this time is we are not going to have a Cartesian product with the entire V, but we're going to have a Cartesian product with just the destination vertex itself, which is just the set of E in this case in it. And we are still mapping everything to R asterisk, because that is representing all the non-negative real numbers. So this is the modified h that we can use. So this way I don't have to kind of define all of the other heuristic functions. or the other heuristic values, because they're not useful to me. Is that okay? Does everybody understand how I just redefined the heuristic function by limiting its domain to what is relevant to us? All right, cool, thank you. All right, so with that out of the way, let's get back to the algorithm. So now we're getting to the for each, which is the 1, 2, 3, 4, 5, 6, the sixth bullet from the top. And this is the initialization. So in the initialization, instead of just having the L value, in Dijkstra's algorithm, we have two values associated with each vertex that we have to initialize. So the first part that says for each lowercase v in uppercase V, do initialize it. That means every single vertex of the graph is going to have a G value and also an F value initialized. And if you look into the for each loop, it has a conditional statement nested in it. And the conditional statement basically just differentiates whether V is our source destination or not. So I'm gonna put I'll put the algorithm back into view for now, because I want to point out the part of the sentence that is relevant to our discussion. All right, so if V does not equal to S, which means it is not V, if V is not a start vertex, then we'll initialize G and F both to infinity. And here is an explanation of what G of V is really representing and what F of V is representing. G of V is representing the actual length of the shortest known path from vertex S to vertex V in this case. So vertex S is our start vertex. So if it is anything other than the start vertex itself, since we have not really explored any edges, we'll just say, we do not yet know whether there really is a path from vertex S to vertex V. And as a result, the G value is going to be 0, because we don't even know whether there is a path or not. And then F of V is kind of the same thing, but it's not, okay, because it has an extra component. The extra component is it is the estimation of the length of the shortest path from vertex S, the start vertex, through vertex V, which is the parameter itself, to vertex X, which is our destination. So so the F value is not the same as the G value, because it includes that extra component of the estimate from vertex V to vertex X using the heuristic function itself. All right, so do we have any questions at this point? I'm not seeing any questions in the text channel. Okay, so let's move on to the else case. The else case is easy, because the else case means V and S are the same. In other words, we are talking about the start vertex itself. So the first question is, what is the length of the shortest known path from vertex S to vertex S itself? The answer is going to be 0, because it is the same vertex. We are already there. So that's a fairly simple question to answer. But the slightly harder question to answer is, what is F of V? So when you look at F of V, you have to remember what it is representing. F of V is representing the estimated length from the start vertex S all the way to the destination vertex X through vertex V. Now, in this specific case, V is S. Okay, so it's not a very smart question to ask, right? Because it is really asking, what is the estimated length of the shortest path from vertex S through vertex S to the destination vertex X? Well, the answer is just h of sx, because that's what the heuristic function is for. It is just a very easy to compute kind of thing that will allow us to have an estimate of the length of the shortest path between two vertices, and it cannot be overestimating. So that's why f of v, when v equals to s, f of s is actually just h of sx. That's kind of easy to understand. All right, one more thing to initialize. There's a prev function here. So the prev function is basically a back pointer that will allow us to reconstruct the shortest path. And the way we reconstruct it is from the destination vertex all the way back to the start vertex. So, and by and in order to do that, we need a reverse, a way to reverse the whole process. So we need to know, what led us to vertex V. And initially, because we don't even know whether there are actually any edges within the graph, so prev v is initialized to be undefined because we don't even know, whether there will be an edge going to vertex v, and that is regardless of whether vertex v is is the source or the destination or any other vertex. Because if there are no edges in the entire graph, then everybody is going to have a prev v of undefined. And nobody says that the start vertex cannot be the destination of an edge from another vertex. That's perfectly permissible. It's just that it's not very useful, in our computation, but it's perfectly allowed in this case. All right, so let me see if there are any questions. I'm not seeing any questions from the text channel, but I just want to make sure. I think there's one person watching the YouTube side, and there's a longer lag time from YouTube compared to Discord. Oh, I take it back. There are 5 people watching from YouTube. So, okay, all right. But I'm still not seeing any text messages on Discord, so I'm going to move on. All right, so the next line, which is let O, get the set with just S on it, that is our starting point. Okay, so in a way, uppercase O as a set is doing what Q is doing in Dijkstra's algorithm, sort of, okay, but it's not exactly the same thing, but it has kind of the same feel to it. But you can still kind of apply the same understanding that whatever vertex has just gotten an update for its G or an F and prev value is the one that needs to be added to the set O. Okay, so you can kind of still use that method to understand what makes a vertex appear in O. Now in this case, it's just initialization because we haven't started to run the actual while loop yet. But we can definitely see how the start vertex is special compared to all of the other vertices because it is the only one that has a non-infinity G and F value. That is why S as a vertex is special, and it is our starting point. So remember, in Dijkstra's algorithm, we start from the destination vertices and work our way back to all of the other vertices. In the A-star algorithm, we start with the start vertex and then work our way to the destination vertex. So that's also a difference between the two algorithms. So do we have any questions before we get to the while loop, which is the next statement in the algorithm? Because we are right about to get to this point. So right now I'm not using the graph as an example yet because I just want to generally describe the algorithm before we go ahead and trace it. All right, I'm not seeing any questions. All right, so we'll get to the while loop here. Now, the while loop of Dijkstra's algorithm is fairly simple. As long as Q is non-empty, do the following, right? So it's pretty easy to determine whether a set is empty or not because if it has no elements, it's empty. Okay, that's pretty easy. In this case, it's a little bit different because the condition is a quantified statement that says while there exists lowercase v in O is our set, f of v is less than g of x, do the following. Okay, so the condition is not asking whether O is empty or not. Okay, we are asking, can we find a vertex in O, which also means if O is empty, the condition is going to be false and we can get out, okay? So O being empty is definitely one way to get out of the loop. But that's not the only way to get out of the loop, because we have to be able to find at least one vertex V in the set O such that the F value of V is less than the G value of X. All right. Let's think about what this means. Okay, well, we are focusing on just this comparison here. What does it mean when f of v is less than g of x? First thing that needs to happen is, do you remember what is f representing and what is g representing? Now those are all explained up here, right? So if you had studied, or read this algorithm ahead of time over the weekend, you might have some of that already in your mind, because once you have read it, you go like, oh, okay, so f is the estimated length of the entire shortest path from the start vertex through vertex v all the way to the destination, whereas g of x is the actual length of the shortest path known up to this point between the start vertex and vertex x. Because vertex x is our destination, that means, oh, this is the length of the shortest path that we have found up to this point from the start to the destination vertex. All right, so given that we know the semantics of f versus g, why is it important that we have to be able to find at least one vertex v such that f of v is less than g of x? So to understand this part, we just have to reverse the condition. We look at the flip side of the condition, which basically says, yeah, we got a bunch of vertices in O, but none of them, okay, none of them has the f value being less than the g value of x. In other words, all of the f values are greater than or equal to the g value of x already. Why would that be significant? And Aiden just posted something. So it's checking whether there is any heuristic path or any path that involves a heuristic value that is shorter than the length of an actual path already found. Yes, so Aiden is correct about that. Because if the estimated, which is always guaranteed not to overestimate, so if all the estimated length of path from the start vertex to the end vertex are greater than or equal to the length of the shortest known path from the start vertex to the destination vertex, I can exit right away, because the actual length of those paths are guaranteed to be at least as long as what they're estimated to be. So if the estimates are already greater than or equal to the length of the shortest found path from the start vertex to the end vertex, I can stop right there, because I know at that point that I cannot find any shorter path. That is the rationale behind this condition. Then somebody's going to ask and go like, well, do we have to do it this way? Can we just check whether O is empty or not? The answer is, it is not wrong to simplify this condition to check whether O is empty or not, but you might go through more iterations of this loop than you have to. So in order to make this algorithm more optimized, the condition to get out of the loop should be like this. So this way, once we know there are no shorter paths than what we have already found, we just exit the loop. There's no need to burn extra cycles on the computer when you already know that any additional iterations through this loop is not going to give you a better answer. So next question, somebody's going to ask that question. In the final exam, if I give you a question about A-star algorithm, and if that algorithm looks exactly like this one using this condition, is it okay for people to simplify this condition to simply whether O is empty or not? The answer is no. Okay, whatever algorithm I give you in the final exam is the algorithm that you have to follow. So I hope I make that extra clear at this point of time. So by the time that we actually have the final exam, there won't be any question, any need to clarify that point. All right, so once we get into this loop here, once we get to the let C in O blah blah blah, what does that mean? Well, that means we know at least one vertex in O is a through point, is a via point from the start vertex to the end vertex, where the estimated length of a path, of that particular path, is less than the length of the known shortest path from the start vertex to the end vertex. You go like, woohoo, yes, that is cool, because that means we still have hope to find a shorter path from the start vertex to the end vertex, to the destination vertex. But there may be more than one of those vertices. In other words, you might have several candidates, where they are all possible vias, okay, VIA, vias, from the start vertex to the end vertex. If that is the case, which one should I choose? So this statement here, the let statement, right, the first statement inside the while statement, that basically says, let's look for the most promising one, okay? In other words, amongst all of the vertices in O, I want to find the one that has the least value. Now, there may be multiple ones with the same value, and they're all, less than all of the other vertices. In that case, you just pick one of those, okay? There's no need to fuzz about, okay, since vertex A, B, and C, they all have the same f value, and those f values are less than all of the other f values of elements in the set O. In that case, just randomly pick one, okay? It doesn't really matter which one you pick. So do we have any questions about the let statement inside a while loop? Okay. So this by itself is also telling us that this is also a greedy algorithm. It is basically looking at the most optimistic possible solution and go like, let's check that first, okay, because that looks the most optimistic. So greedy algorithms is really a misnomer, because it should be called the optimistic algorithm, because it's basically looking at the most promising choice and go like, let's check that out first. All right, so Aiden just posted something. Can you make the let C statement be a for each C statement? No. I'll tell you why. Okay, so the answer is no, because if you turn it into a for each, so let me explain the context of what Aiden is suggesting. Okay, so the context is what if we have multiple vertices in O that have the same f value, and all of those are less than the other f values of other elements in O. Okay, so that's the scenario that we have to think about. This statement here says, using the word let, means pick one of those. Okay, pick one of those, and we'll proceed with the rest of this algorithm. What Aiden is suggesting is changing the let to a for each, so that becomes a loop by itself. So we are now obligated to evaluate every single one of those. So the answer is no, because we might be able to find a shorter path already that invalidates all of the other one. Then we don't have to evaluate the other one, which is what Aiden is probably just typed here. Yes, exactly. So what Aiden typed right after the substitution of the let with a for each is the right answer. Okay, because once we go through one of them, depending on which one we go through, we might have found a shorter path. So once we have found a shorter path, that will decrease the value of g of x, which means the other ones may not be valid anymore. They may not even be a good choice anymore. Okay, so once again, it is not wrong. Okay, so if we change this word let into a for each, and then change the indentation accordingly, so that we basically just have one more level of loop, it is not wrong. It is not like changing the algorithm like that is going to change. It's going to either not find the shortest path or find a path that is not the shortest. Okay, because those two would be wrong. It would not be wrong, but at the same time, some of those extra iterations can just be burning cycles, because because once we have updated the f value, the g value of x, because of the one that we have chosen, we might, the other choices that originally looked as attractive as this C may not be on, we can confirm that they are not on the shortest path anymore. So that's the reason why we don't want to turn it into a for each loop. So we just pick one, and now if you're just picking one, then you're leaving certain things to chances, because you might pick one where, oh man, I just checked this out and it doesn't give me a shorter path to from the start vertex to the vertex x. That might happen, okay? But at the same time, you might be lucky and pick one where it just finds a shorter path from the start vertex to vertex x, thereby changing g of x, thereby invalidating the other ones that had the same f value, because they would no longer be less than g of x at that point. All right, so that's okay. All right, so given that we are not changing the algorithm and we are maintaining the algorithm exactly as it is, okay, we are just picking one of those and we call that vertex C. So now we want to see what we're going to do with vertex C. So remember, C is not actually the vertex, it is a variable containing a vertex, okay, that meets this requirement. So the first thing we do is we remove C from O, okay, which is kind of the same thing that we did in Dijkstra's algorithm. Whatever we pick out of the set, we just go like, okay, let's remove it from the set. And then the next one is also very similar, except it's the opposite direction. So this time we're saying for each neighbor n, lowercase n in V, such that Cn is an edge in E, do the following. So before, in Dijkstra's algorithm, we're looking at all the incoming edges to the vertex that we have selected out of Q. In the A-star algorithm, we're looking at all the outgoing edges from the vertex that we have chosen, which is vertex C. So n is bound, because of this for each statement, to be the one of the outgoing or one of the destination neighbors of vertex C connected by an edge. Okay, so from so in the rest of the algorithm, we know what is vertex C, we know what is vertex n, and we're going to do some computation. The first one we do is a temporary variable t, and all t is going to do is to compute g of c, and we add to it the distance of the edge Cn. So all that is going to say, that's all that is saying is, since g of c is the actual length of the known shortest path from the start vertex to vertex c, and Cn is an edge, so g of c plus d of Cn is telling us what is the length of a path from the start vertex through vertex c to vertex n. That is what t is representing. Now, so the question now is, have we just found a shorter path from the start vertex to vertex n? That is the question. So that's what the next sentence is saying. Okay, so the if statement inside the for each loop is asking, if t is less than g of n, in other words, if the length of an alternative path through vertex c to vertex n has a length that is shorter than the length of the known shortest path from the start vertex to vertex n, then we got some work to do, because we have just found a shorter path from the start vertex to get to vertex n. Now, vertex n is not necessarily the destination vertex, but every time we find a shorter path to a particular vertex, we might want to take note, right? Because that vertex may very well be on the way to the destination vertex. So that's why when we find a shorter path to a vertex from the start vertex, we need to pay attention. So what do? Kind of the same thing, but sometimes in opposite direction compared to the Dijkstra algorithm. The first one is not. Okay, the first one is just saying, okay, let's just update the set O. So now we include n in O. That's because we are just about to we are just going to update g of n with a smaller value, and that is the reason why we have to put vertex n in the set O, because that can potentially also impact the outgoing all the vertices connected by outgoing edges from vertex n. That is the reason why we have to add vertex n to O, because now we need to explore all of the neighbors of vertex n. Next thing we need to do is to update pref of n to c. We are just using this to remember how do we go to vertex n. So pref of n being c, all it is saying is, well, in the shortest path, in order to get to vertex n, you have to go from vertex c. That's all it's trying to remember. That's what the pref function is about. So the most important part is to update the g value and the f value, because the pref value is really just for backtracking so that we can find the shortest path again. But the g and the f value is being used, up here and also up here, so that influences, basically how the algorithm works. So g of n is updated to t because that makes sense. Okay, we have just found a shorter path to vertex n, and we need to find, okay, what we need to do is to update g of n to the length of that alternative path, so the g of n is once again representing the length of the shortest path from the start vertex to vertex n. F of n is, in a way, it's pretty easy to understand once we know what is g of n. F of n is just an estimate. It is just an estimate of the shortest path from the start vertex through vertex n to the destination vertex. Well, we are already halfway there because we already know the length of the shortest path known up to this point from the start vertex to vertex n. That's what g of n is. So we just have to add to that amount the heuristic value from vertex n to vertex x. Remember, x is our destination vertex. So we are just saying, okay, 1/2 of this we know, that's an exact number. It is the exact length of the shortest path known up to this point from vertex s to vertex n. So that part is not an estimate. Okay, that part is something that we know. It's a concrete number. The other half is guesstimate. The other half is just going like, well, according to TAC, who gave me some hint, so that's the other way to look at H is hint, okay? Instead of heuristic, you can look at it as a hint. So the hint is, well, TAC told me that, this particular value is going to be always less than, it's always going to be less than or equal to the actual length of the shortest path between n and x. But, since I just need to do a guesstimate, okay, I'm just going to add it. So when you look at the sum of g of n and h of nx, that becomes the estimate from the start vertex through vertex n to get to the destination vertex. It doesn't mean it's going to be the shortest path. It simply means I'm guesstimating if you have to go through vertex n, the shortest path is probably going to be something like that, okay? Or this is going to be the underestimate of the length of that path. Well, I shouldn't say under, because under implies it has to be less than, but it can be equal to in this case. So that pretty much concludes the main logic for the while loop. The next one here is really just backtracking the vertices, so that we start with the destination vertex, and then we use the pref as a back pointer so that we can basically trace our way back to the start vertex. Then we can establish the actual path from the start vertex to the destination vertex, because most of the time we are not really just interested in the length of the shortest path. We actually want to know what the path is. So that's why we kind of need to trace our way back to the start vertex, so that now we can say, see, this is how we go from A to B to C to D and so on. So that's kind of the gist of the algorithm. Do we have any questions? Or are we all completely lost in the description of the algorithm itself? I sure hope that But that is not the case. But if that is the case, I'm gonna have to re-explain things a little bit. All right, I'm not seeing any questions. All right. Oh, here comes one. Yes, absolutely. That's the whole point. I'm going to go through the example that I have presented here. So that's exactly what we're going to do. Yeah, I think so. I think the example can help clear up the concepts. Okay, there we go. So I'm just moving things around a little bit so it just presents better when you watch the video. When you watch the video, you probably still want to have the graph open up, on one portion of your screen, and have the spreadsheet to open up, on another part of your screen, because I think that's just going to be super helpful. And I can make this spreadsheet a little bit wider, but I don't. Yeah, I can actually extend it all the way. No, I cannot, because I can do it a little bit more, and then I can make the tablet window always on. All right, there we go. All right, so we got a few people typing after that. Okay, very good. Are you guys telling me empty words is not going to cut it? Yeah, absolutely. Go ahead, Aiden. Just go ahead and send an animation from Wikipedia. Okay, I guess I have to put my cursor over there. Yep. Now that's a very idealistic kind of situation, where everything is kind of geometric. So the A-star algorithm that we are talking about here, or this particular example, we are not talking about anything that is it's not a two-dimensional thing. So I think the animation gives people a general idea, but I would not be hanging on to that one too much. It's a good way to visualize. Yes, you can use an A-star. No, I take it back. Aiden, you can use A-star whenever you feel like it. You don't even need a heuristic function, because you can always define your heuristic function to map everything to 0. Yes. In that case, you sort of have a heuristic function, but you actually don't. You're still doing uninformed breadth first search when the heuristic function maps everything to 0. So in that case, you basically degenerate to Dijkstra's algorithm, but that would be Iraj's version of Dijkstra's algorithm. All right. Yep. Okay, that's exactly what Aiden typed. I was looking at the screen. I wasn't looking at the text. Okay, and then Garrett typed, I was eventually going to ask which algorithm works best in something like Google Maps. So in Google Maps, I'm not sure exactly what they use. I think it's a little bit more complicated than what we are just talking about here. But in the map, generally speaking, you can use a heuristic function, which is just the distance of a straight line between 2 points, because you cannot, short of any portals, okay, you cannot actually travel less distance than this distance of 2 points in the straight line. So that usually gives you first of all, that heuristic function is very easy to compute, and 2, it is always not going to overestimate. So that would actually be a good heuristic function to use when you're calculating distances on a map. But Google Maps does not take, it's not just distance, it's also time. But time, even if you factor in traffic and all kinds of stuff like that, can still be, I guess you can still guesstimate, by using the traffic speed at the lowest portion of that region and then use that combined with the straight line distance, you can still come up. Oh, no, I take it back. Not the slowest, it's the fastest. Okay, because you want to underestimate. So if you look at that region of a map and you say, okay, what is the fastest average speed on the street, and then use that as a velocity, and then you look at the shortest the the distance between the distance of the straight line between the 2 points, and then you use it to calculate the time, that would always be not overestimating, right? So I suppose you can do something like that. Exactly. Yep. 2D works just like 3D, except you have Z. Yeah, you can always plug in some unrealistic, speed. But in that case, if you plug in a number that's too big, like if you're grossly overestimating the speed, then you might end up losing enough information where the search becomes, more or less like Dijkstra's algorithm. So it's not as informed anymore. All right. So this is kind of interesting because you guys can see me looking off the screen occasionally because I have a package coming that requires a signature. So I find it very kind of coincidental because that's UPS using some kind of algorithm to try to optimize their truck stops, to find out what is the best way to go around. And the other part that is interesting. Oh, okay, that's cool. Thank you, Liu. So the other thing that's interesting about UPS is if you just follow that truck around, because you're getting a package, on that day, you will find that it's not exactly in a quote unquote systematic way that you can like, oh, it's just traversing like this or it's traversing like this. So UPS has their own algorithm to find out what is the best route for a truck to go through all of the stops. So I find that to be quite interesting too. The traveling salesman problem is different in a way. Yeah, it is. Okay, I take it back. Sorry. Yeah, it is the traveling salesman problem because now you're not just concerned about one point and another point where everything in between doesn't really matter. Now it becomes a problem where you have to go through certain points, right? And you're trying to find a path that you can go through, all of those points. You can traverse every single point, but you want to find the shortest path so that you can traverse all of the points. Yes, that does become the traveling salesman problem, which is NP complete. And I believe I talked briefly about NP completeness in a previous lecture. So the traveling salesman problem is the classic problem of that entire class of problems known as NP complete. So that is correct. Jack is correct about that. Yeah, so A star would not be very suitable as a delivery route planning unless there's only one destination. That's it. Yes, the left turn thing is interesting because I think it's Mythbusters. Okay, Mythbusters, basically did an episode on whether minimizing left turns, can help minimize the cost of delivery. So what they found was interesting because what they found was if you're driving something like a Prius, it actually does not have any impact in San Francisco. But if you're driving a delivery truck, it does have an impact. Or was it the other way around? I cannot remember, but it does make it. Okay, so the difference has to do with whether idling is costly or not. That was actually the deciding factor. So if you think about it, a diesel truck, with a diesel engine, when that engine is idling, it actually does consume quite a bit of fuel compared, relatively speaking. It's not going to be a whole lot less than the truck not moving. But when you look at a Prius, if the Prius is not moving, it's consuming maybe just a little bit of electricity to keep the AC and the fan running, but it's not really going to be consuming a lot of energy. So that turns out to be the deciding factor or the one thing that makes it economical to have trucks to only make right turns. So that was you guys can watch it again. I cannot remember all the exact details. Yep. And of course, in San Francisco, it's also a little bit different compared to Sacramento, because a lot of places where they only allow right turns, a lot of places have no left turns, and then they have a lot of one-way streets and stuff like that. So optimizing a route in San Francisco, it's really kind of interesting. I mean, it's going to be the same algorithm as any other town, but the route that is the resulting route is interesting because it takes into consideration of all of those things. Cool. Yeah, most hybrids will auto stop, but they still have the AZ running. Not that you need it very often in San Francisco. All right, so getting back to this algorithm, so we need to track stuff, right? So a few things we need to track for sure. We have O, the set. We have C, which is the vertex that we pick out of O. And then we have N, which is an outgoing neighbor of C that we are considering to see whether N can use any updates, right? So now we have the three functions that we are talking about. So there's the G function, there's the F function, and then there's the pref, okay, the previous function. Okay, so at this point, there are many ways to represent a function. So, with very few, very few vertices that we are dealing with, we can basically have one column per, value. That just makes it easier for us to track, when we are looking at it. So under G, we have G of A, G of B, G of C, G of D, G of E. And then we group all of these under G, and then we do the same thing with F. All right, so the laziest way to do this is, oh wait, this is not laziest yet, okay, so this is going to be lazier. So we go to Format, go to Merge Cells, Merge All. All right, there we go. All right, so all we do is now we copy, and we paste, and then we paste. So the idea is we have F over here, and then we have pref over here. So that just makes it easier for us to find which column we need to update, and instead of just copy and pasting the whole set, which is going to be time consuming, this is nice, easy to look at. So we're going to do it this way. All right. So now we go back to the algorithm. So hopefully you have the algorithm, on somewhere on your screen, so that I can just, kind of focus on the spreadsheet on my screen. All right, so we're going to do the initialization. So G, F, and pref, they all have to be initialized. And I'm going to highlight which one is our destination. Vertex E is our destination. So I'm going to highlight all the E's over here. So we got 1, 2, 3, boldface. There we go. So all the destination vertices, or the only destination vertex is highlighted. But to us, it's not the destination that is important, it's the start vertex that is important. So vertex A is our start vertex. And I'm going to have a special symbol to look at it, to see it, because I think it is kind of important that we kind of remind ourselves, which one is the beginning, which one is the end. And for the beginning, I suppose we can use italic or some other way to, or we can change the color of the text. I'm going to use green here. So green start for the beginning, and then red for the stop. There we go. So start and stop color-coded. Alright, so end is going to be reddish. There we go. There we go. Alright, so color-coded. Now, if anyone in class is has color blind and cannot tell which color is which color, they'll let me know. Alright, so now we're going to initialize the G values. So according to the algorithm, the start vertex is the only one who's going to be getting a 0 for the start number, and all of the other ones are going to get infinity. So we'll just go ahead and copy, paste, 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 paste. Okay. And for for f of a, sorry. So for f of a, it has to do with the heuristic, which is defined here. The heuristic value between a and e is 9, so f of a is 9 to begin with. Now for prev, every single one is going to be unknown. So I'm just going to use a UNK for unknown. There we go. Oops, I just clicked the wrong key. There we go. Unknown. There we go. So that's how we initialize the three functions, and now we have to initialize O with the start vertex, which is vertex A itself. Alright, so this is our starting point. Actually, I should put this in the previous row like this. Oh, no. Okay, never mind. Just gonna type it over. There we go. Get rid of that. Alright, so this is our initial condition. Now we get to the while loop. So the while loop says, are we going to exit right now? The answer is no, because we have at least one vertex in O, and on top of that, the f value of A, which is 9, is less than the g value of x, which is currently infinity. So we do meet the condition specified by the while loop, so we have to get in the while loop. So now we have to select which element in O should become our vertex C. Well, that's an easy one because we only got one element in O, and we already know that it has a value that is less than g of x, so we'll start with that. So variable C is going to get the value of A. And then we have to look at all the outgoing edges from vertex A. So over here we can see there are two outgoing edges. One is going to C, one is going to B. And once again, at this point, it doesn't really matter which one we choose. It would not really change the outcome of the algorithm. So we're going to choose C first, okay? There's nothing that says I cannot choose vertex C. So now we're looking at the edge AC. So I forgot one thing. I forgot local variable T. So I'm going to have to insert one to the left. Now we have to keep track of T as a temporary variable. So T is basically G of A in this case, plus the distance of the edge AC. The distance of the edge AC is 5. So we are looking at 0 plus 5, which is just 5. Alright, so T is 5. And now we go into the conditional statement of the algorithm that asks, is t less than g of n? T is 5, g of n, remember n is c, so when you look at g of c, it is infinity. 5 is less than infinity. Yep, that is true. So once we get into the algorithm, the first thing we do is we add vertex c into the set. Oh, by the way, I forgot about this. Okay, once we choose A, out of O, we have to remove vertex A from O. But at this point, we're going to add C into the set O, and then we're going to do some updates because G of C is going to be updated to just 5, and then F of C is going to be G of C plus the heuristic from C to E. So the estimate from C to E is 5. 5 plus 5 is 10. So the F value of C is 10. And then the prev of C is going to be A. Basically, when we backtrack, we can say, well, to get to vertex C, we are coming from vertex A. So that completes one iteration of the for each loop. Now we are ready for the next iteration of the for each loop to explore another outgoing edge from A, which is from A to B in this case. So now we're looking at g of A, which is 0, plus the distance of AB, which in our graph has a distance of 1. 0 plus 1 is 1. And now we have to compare that 1 to g of B. G of B is currently infinity. 1 is less than infinity is true, so we have to get into the loop to update a few things. So the first thing we do in the update is to add B to O. So O now has C and B in it. The second thing we update is prev. So we say in order to get to vertex B, we're going to have to come from vertex A. And then we update G. G of B is going to be just 1, which is T itself. And then f of B is going to be G of B plus the heuristic from B to E, which according to my misleading heuristic here is 0. So this makes G of B and f of B exactly the same, which is 1. So are we still doing okay at this point in terms of tracing the algorithm? Alright, looks like everything is still okay. Alright, so we're going to move on because now we have looked at both outgoing edges of A. So now we have O having elements C and B in it, or B and C, it doesn't matter because it's a set, ordering is not important. So now we have to ask, does at least one of these vertices have its f value being less than the g value of our destination, which is E? The answer is, well, yeah, both of them actually, because the g value of E is still infinity. So now we have to go back into the loop, and we have to say, okay, pick one of those two. Okay, choose one of B and C, as variable C. Well, we have to find the one that has the least f value, and turns out B has the least f value because the f value of B is 1, the f value of C is 10. So we're going to choose B in this case. And then we have to make sure that we remove vertex B from O so that we don't re-exploit unless there's a reason to. So now we have to look at all the outgoing edges from B, and there are 2. So we'll look at vertex C first. Okay, so we go to vertex C first, and this is already kind of interesting because guess what? We found a shorter way to get to C. So okay, I said that I talked ahead of the algorithm. So first of all, we have to compute T. So T is going to be G of B plus the distance of the edge from B to C. So we're looking at 1 plus 3, which is 4. And now we have to compare T with G of C. So G of C is not infinity. We updated that to 5 already, but 4 is less than 5 is true. So we have to get into the then branch of the conditional statement, and this is the fun part. Okay, we're going to have to add C into O, but that's okay because it already has C in it, so it doesn't really change O by much. And this is the other interesting part, is we have to update the prev of C. So prev of C used to be A, and now it is going to be B, okay? Because we just found a shorter path to vertex C through vertex B. The third thing we do is to update G of N. That's one of the easiest steps to do because we are just copying T to G of C in this case. So that's updated to 4. And then we have to update the f value too. So the f value is now the g value plus the heuristic value from C to E. The heuristic value from C to E is still 5. So we are basically talking about 4 plus 5, which is 9. So we put a 9 here. And there's one more outgoing edge from B. The other outgoing edge from B is going to vertex C. Oh, we just look at the C, so this one goes to E. Alright, so we put E over here. Now, E is indeed the destination vertex, but we don't treat it any differently. Okay, the algorithm does not treat vertex E any differently when it comes to the evaluation of the functions, the values, and so on. So just like the other one, we look at G of B. G of B is 1. And then we add the heuristic value from E to E itself. Nope, I take it back. Never mind. Okay, I misspoke. I misspoke. We look at the g value of b, and then we add to it the distance of the edge from b to e, which is 20. So that makes t 21. And now we compare this 21 with the current value of g of e. The current value of g of e is infinity. We have not yet updated g of e. So when you think about, okay, 21 versus infinity, yeah, 21 is smaller. So now we know that we have to go to the then portion of the conditional statement. So the first thing we do is we add e to the set O. Okay, I think my package is here. Give me a second. I'm gonna go to the door. I'll play with it later. All right, I'm back. Okay. I apologize for having to, pause the class just a little bit. But that's actually beneficial, because now I can show you why this way of tracing an algorithm is good. Because you can see how I can come back here and I can see where I'm at. In CISP440, I will actually write down the line number of the algorithm too, so I can actually go back to exactly where I left off. But in this case, I still remember where I was talking about earlier, in just a few minutes ago. So I can just follow that up. All right, so we just added e to the set O, and now we have to finish up the rest of the updates. The next one is going to be the pref. So we look up the pref of e, which is currently unknown, and we update it to vertex b, because we get to vertex e from vertex b. So that is going to be updated to b. And then the next one is going to update g. So g of e was infinity, and now it's going to be updated to the same value as t, which is 21. Wrong column, I guess. All right, so here we go. Here's 21. And now we have to update the value of f of e. So the value of f of e is the value of g of e plus the heuristic from e to e. But the heuristic from e to e is 0. Now that really should not come as a surprise, because the h value is an estimate of the length of the shortest path from a vertex to a vertex. In this case, it's the same vertex, so the length of that shortest path is going to be 0, because the heuristic value cannot be more than the length of the shortest path, so it has to be 0 too, because it cannot be negative. So that's good. That means the value of f of e is going to be 21. Oh, okay, I just moved the wrong item here. There we go. And zoom out. Oh. Huh. Okay, zoom out. Zoom out. And one more time. That is too much. Okay, give me a second to Alright, so it doesn't want to. It will still fit the screen right now, so that's fine. I'm going to put 21 over here. Alright, so that completes the update to the algorithm, to all the columns. Do we have any questions about this particular step? Okay, so it's not any different from all of the other steps. So now it's getting more interesting because now we go back to the while loop. We look at the set O, which has elements C and E in it, and we have to ask that question again. So the first question to ask is, does at least one of these two vertices have a f value that is less than the g value of the destination? Okay, so we are focusing on the f value here. F of C has a value of 9. The f of E, on the other hand, has a value of 21. And we are asking, does at least one of these two vertices have a f value that is less than, not less than or equal to, it has to be less than the g value of E, which is 21. So now we have identified that, oh yeah, sure, vertex C meets that requirement because f of C is 9, which basically means if I were to estimate the length of a shortest path from the start vertex through vertex C to the destination vertex, it will be 9. And that is currently less than g of E, which is 21, which is basically saying the length of the shortest known path up to this point from the start vertex to the destination vertex is 21. So that means there is still hope for me to find a shorter path to the destination. Okay, because I found a path already. It's just that it may not be the shortest path according to what the estimate is telling me. So once we say that yes, we have to perform at least another iteration, we get in. Now we have to select which vertex we want to put into variable C. So that part is easy because it's really just looking at the f value of the elements in O. So we got 9 versus 21. Okay, 9 is the smaller one, so that's the easy part. So now we have variable C containing vertex C. Now we have to look at all of the outgoing edges. Oh, we have to remember to take it out of the set O, and now we have to look at all the outgoing edges of vertex C. So we look at vertex C. You guys can see that on my screen here, or you can just look at your own. From here on, it's fairly simple, because C has one single outgoing edge to vertex D. So now we look at look at the value of T. We have to initialize it, which is g of C plus the edge, the distance of the edge going from C to D. G of C is 4, and then 4 plus 4 is 8. So we are looking at a value of T for 8, and then we compare T with the G value of D. The G value of D is still infinity right now, so we know that we have an update coming up. So now we add D to the set O. We update the previous of D to be C in this case. We update the G value of D so that it's the same as our T, so that's just 8. And we also have to update the f value of D so that it is the G value of D plus the heuristic from D to E. The heuristic from D to E is 1, so it is 8 plus 1, and that makes it 9. And that's it. Okay, we only have to go through one iteration for the for loop because there's only one outgoing edge from C to D. Now we go back up to the while loop. So the while loop looks at O and go like, can I find at least one element in the set O that has a f value that is less than the g value of the destination, which is E? So we look up f of D. F of D has a value of 9. We look at the f value of E, which is 21, and then we look at the g value of E, which is also 21. So we know the g value, the f value of E is not less than the g value of E, but that's okay because we found that the f value of D is less than the g value of E, so there's still hope for me to find a shorter path. So at this point, I choose D out of the set because which one I want to use is just dependent on the f value. So we are comparing 9 versus 21, and 9 is the smaller value. So that's why we choose D out of the set, and then we remove it from the set. And now we have to look at all the outgoing edges of D, and there's only one. D only goes to E using an edge that has a distance of 1. So we look at E as our outgoing neighbor, and then we have to compute E. T, sorry. So we have to now compute T. The value T is based on G of D in this case, which is 8, plus the heuristic from D to E, which is 1. 8 plus 1 is 9. And now we have to, oh no, I take it back, not the heuristic, it's the actual edge. Okay, it's the distance of the edge that we are adding to the G value of D. It is not the heuristic from D to E. They turn out to be the same in this case, okay, but the value that we are using is the actual distance of the edge. Okay, so I should be correcting myself about that. It turns out to be 9 either way. Alright, so we now take this value of 9 and then compare that to the G value of E. The G value of E right now is 21. 9 is less than 21 is true. So we have to go through the then portion of this conditional statement. First thing we do is we update the set O. We basically want to include element E in the set, which is already in there. Okay, so there's no visible change to the content of the set O. And then we update the previous of E, which was B before, and now it is D. And then we update the G value of E from 21 to 9, because we are just copying the value of T to the new G value. So that's just 9. And we also have to update the F value. And the F value is also 9 because we are adding the G value of E to the heuristic between E and E. So, and that has to be 0 because they are the same vertex. And as a result, we also have 9 over here. So now we are getting out of the for each loop because there's only one outgoing edge from vertex D. And now we are back to the while loop. The while loop looks at the set O, and it's going to ask the same question. Do we have at least one vertex in O where the F value is less than the G value of E? So we just, now I know, okay, I know, you already know that. No, we just updated the F value of E is the same as the G value of E, and therefore it cannot be less than. But we're just gonna do this anyway. So we look at the F value of the only element in O. It has an F value of 9. We look at the G value of the destination, which turns out to be E also, and it also has a value of 9. 9 is less than 9 is not true. So that means even though O is non-empty at this point, we can get out of the loop. And when we get out of the loop, we still have one element left in O, and that's okay because we know that we cannot find a shorter path at this point. Nothing looks promising anymore. Alright, so let me check and see if we have any questions. I know I just went a little bit over time, but I felt it was kind of important to kind of go through this. And I will use 30 seconds to show you how to use the pref, and then we are done for today's lecture. But first of all, I want to see if there are any questions. No questions. Alright, so now we use the pref. So the way we use the pref function is to start with the destination. So in this case, we are starting with the destination of E. We look up what is the pref of E. According to the spreadsheet, the pref of E is D. So we know this edge is part of the path from the start to, from the start vertex to the destination. Then we move up to D and we ask who is the pref of D. The pref of D according to the spreadsheet is C. So we know this edge is on the shortest path. And then we get to C and we ask who is your pref. Now this one is a little bit more interesting because we actually get two options here. We get A and we also have B. But if you look up the spreadsheet, the pref of C is B. So we use this edge over here. And then we go to B and we ask who's your pref, and A is the pref. So we highlight that edge. And then we go to A, and A does not have a pref. Okay, the previous of A is still unknown because, well, because it's the source or the start vertex. So this is when we can stop and conclude that the shortest path from A to E is from A to B to C to D and then to E. So that concludes the trace. So I hope this helps a little bit. And we can do one homework assignment on A star as well. Okay, so I don't think the one that I assigned last week is due today. I'll double check. Let me double check. So that one is due on the 5th. Okay, so that's due on Wednesday. So on Wednesday, I can give you a new assignment to track down, A star, the A star algorithm, because I think doing it by hand at least once is gonna help. So that's the end of today's lecture. Any questions? All right. Well, if there are no questions, I'm gonna stop today's lecture. Can I restate again that initialize the heuristic function? The heuristic function is really just chosen. I specifically chose these values to be the heuristic function so that it is a little bit interesting, because at some point we thought, hey, B is a good option, and it turns no, I take it back. At one point, it seems to be a good idea to go from C to D, from A to C first, and that turned out not to be a good idea. So in this case, the H values are hand-picked. They are not computed in anyway. So there's no quote-unquote process to the initialization of the H values. All right, Anita is still typing. Okay, so the exam. Well, no, not necessarily. It depends on the nature of the question. So the H values may be given to you. Maybe some of them are given to you, and you have to figure out a few more. So, it's up to the question. All right, and then Li Yu is still typing. There we go. B to E is 0. Nope, that's not. Okay, so when you look at the heuristic function, this is basically saying it's an estimate, right? It's estimating the length of the shortest path from B to E is 0. It's perfectly okay. It's just an estimate, okay? As long as that estimate is not over. In other words, as long as that estimate is not actually longer than the length of the shortest path, it's perfectly okay in this case. Let me see. Would 1 be okay? Between B and E. Yes. So any value from 0 all the way to 8 would be fine as a heuristic value of B to E. But if you use 8, it makes it kind of less interesting. So I just choose a 0 here to make it more interesting, because it seems like this is a good way, right? To go from B directly to E, and that turned out not to be the case. Okay, so here's something you guys can do. Okay, this is something you guys can do. Yeah, you can just play with the heuristic values and see if by playing with the heuristic value, it would change the way we explore the vertices. Okay, so that's one thing you can do before Wednesday. But I will give you an assignment on Wednesday too. All right, so the question is, so the number doesn't depend on the actual graph. Well, it has to depend on the graph itself, in the sense that it cannot be more than the length of the actual shortest path. But other than that, it is somewhat arbitrary. I mean, in order for the algorithm to function, the only requirement is the h value cannot be more than the length of the shortest path between those two vertices. Yep. And other than that, we can just pick a number out of thin air as long as it meets the requirement of not overestimating. All right, sounds good. So I'm gonna check out at this point. I'll see you guys on Wednesday with a new homework assignment. Yep, you too. Have a nice day.